Back here with question 4 for exam 3. Let's get into this question. Long one. The next two are pretty long. All right, so for number 4, explain the mechanism by which fluids normally move out of and into capillaries. Describe the various forces involved, like hydrostatic and colloid osmotic pressure, and how these forces differ at the arterial and venous ends of the capillaries. Then, using inflammation as an example, describe the mechanisms responsible for edema. In part 2 of this essay, describe the baroreceptor reflex, include all the components of the reflex, and describe the chain of events that would occur if systemic blood pressure suddenly dropped. Explain how each of the following is involved in the regulation of blood flow. Myogenic autoregulation parasines include their role in active and reactive hyperemia and sympathetic regulation. All right. It's a long one. It's really a doozy. Really. Okay. So first up, the difference between capillaries and, not the difference, but like what moves fluids into and out of the capillaries, which are the ends of our arteries that extend into tissue, little microtubes that allow certain things to go into our cells. So that's basically what it is. That's where fluid exchange occurs between blood and tissues. And this exchange is governed by our two main forces, our hydrostatic pressure and our colloid osmotic pressure. All right, so the hydrostatic pressure is pushing stuff in. That's our heart pressure, our blood pressure, just pushing things down the tube. Our osmotic pressure is going to be pressure pulling fluid in because of osmosis. So that's pretty cool. So our hydrostatic pressure is generated by our pumping action of the heart, like I said, and that's going to push fluid out of the capillaries and into our interstitial, I think that's how you say it, space, our interstitial space. And at the arterial end of these capillaries, our hydrostatic pressure is higher than our colloid osmotic pressure. And this is basically going to promote filtration of fluid out of the capillary because it's pushing so hard. All right. On the other side of things, at the venous end of things, you see what I did there. Our hydrostatic pressure is going to decrease, and that's because the resistance encountered by the blood flow through the capillaries is going to stop it. There's just so much in the way that our blood pressure just drops off. There's just too much stuff, too much resistance, too much tissue for all of the blood to work through via our hydrostatic pressure. So that's where our osmotic pressure steps in. And this is pressure that is exerted by our plasma proteins. And it stays pretty constant, and it gets more significant as you go. As there's more resistance, more stuff in the way, it's going to be pulling fluid back into the capillary via this osmosis. The proteins are basically what's pushing them, if I didn't say that before. All right, anyways, so that is our first portion. Inflammation as an example, describe the mechanisms responsible for edema. Okay. Come back up to my notes. All right, so first we need to understand what an edema is. Edema, it might be edema. I might just be saying it wrong. Edema. Let's go with that. And if I said edema and that's the correct one, guess what? I've switched it now. Edema. All right, so that is an abnormal accumulation of fluid in the tissues, blood in this case. You could have a hemoedema. So during inflammation, the tissues are going to release our chemical signal that will increase our capillary permeability. And there are different chemical signals that can do that. And this will allow proteins and fluid to leak more easily into the interstitial space. And so that balance between hydrostatic and osmotic pressures is going to be messed up. It's going to be disrupted, and that is going to lead to an increased fluid movement out of the capillaries and reduced reabsorption into the capillaries, and that's going to give us our edema, or really looks like swelling underneath the skin. You can see the blood coming up to the surface of the skin. Sometimes I know that my great-grandma had that, She got edemas really, really easily. I don't know what caused it. Anyways, that's what it is, really. You know, that's the mechanism. It just makes it more permeable, and it lets the fluid through the. Why did I just lose the word? Our capillaries. It lets the fluid through the capillaries into the tissue around it. You know, that pressure is just so messed up because of the difference in fluid flowing through. All right, next portion of this question is the baroreceptor reflex and the components of that and the chain of events that occur if systemic blood pressure suddenly dropped. All right. All right. So our baroreceptors are going to be stretch sensitive. They are stretch sensitive receptors, and they're located in the walls of basically any major blood vessel, like our carotid and our aorta, so on and so forth. The major ones contain these stretch receptors or baroreceptors. And so if systemic blood pressure suddenly drops, like you get stabbed and your blood, the baroreceptors are going to detect this change because they're not being stretched as much. So they're going to send signals to our cardiovascular control center in the brain. And let's see, where would it be? Medulla oblongata, if I remember correctly. And that's going to respond by increasing our sympathetic nervous system activity. And that is going to start throwing the brakes on everything. We're going to get vasoconstriction, a lot more resistance to increase that blood pressure to make up for that lack of blood volume. All right, just because those receptors weren't being stretched as much. I think that's how it works with the stretch receptors. I think if they're not being stretched enough, then we get this of our vasoconstriction following blood loss, blood volume loss. I might be wrong. That's how I understood it. All right. So on top of that, our sympathetic stimulation will actually increase our heart rate and the amount of force in the contractions, and that'll boost our cardiac output, and that will bring our blood pressure back to normal volumes to make up for the fact that we don't have as much blood as we did beforehand. Beyond this, our blood flow is actually going to be regulated by mechanics like myogenic autoregulation and paracrines, which is our next section in this question. It helps regulate that blood pressure and that blood flow. The paracrines and the... I lost my spot again. That's what I should name this channel. I lost my spot, but I'm teaching you something. All right, so our myogenic autoregulation refers to our ability of our blood vessels to maintain constant blood flow despite any changes that are happening around it pressure-wise. Our paracrines, like nitric oxide and prostaglandins, are locally acting substances. You know, they work in small portions throughout our blood vessels and blood capillaries. Yeah, paracrines. Yeah, all right, sorry. Jeez, it's going to be in response to metabolic changes or stress, even sheer stress. So, myogenic autoregulation and paracrines. So, our paracrines are going to increase our vasodilation, which means increasing our blood flow to match the tissue demand. I don't have a good example right off the top of my head, but this process of increasing our blood flow is called active hyperemia. Reactive hyperemia will occur when blood flow increases in response to a previous period of reduced flow, helping to restore normal perfusion after temporary ischemia. So let's put this in weightlifting terms. You know, you go in for your big deadlift, you're maxing, 515. It's 505. Let's throw a number up there. 500 pounds, you're lifting it straight off the ground. It's going to take a lot of blood flow away from your head and into your muscles And at that same time, you're exerting a lot of pressure, so we're going to see vasoconstriction. Where our pericrines are concerned, they are going to increase our vasodilation, giving back that blood flow. So that's going to be our reactive hyperemia, as we're increasing the blood flow to where we need it in our bodies. All right, I think that that covers it. Myogenic autoregulation, hyperemia, active and reactive, and sympathetic regulation. I think that's it. That was essay question 4. Back here for 5. Don't go anywhere.